I want to talk through the different types of weathering. So I'm starting with this slide, which is the beginning of the physical or mechanical weathering. We're doing 3 types of mechanical weathering and 3 types of chemical weathering. So mechanical weathering, again, is when only the physical aspect of the rock is changed. So the rock is broken down into smaller pieces, but there aren't any chemical changes to the minerals. So the first type is called frost or ice wedging. It basically is when water gets into cracks in rocks, and when water freezes, it expands. So it gets larger, and that pushes the cracks open wider. And you can see that in this image here with these little blue arrows showing how the frozen water is basically pushing against the sides of the rock, and that forces the cracks wider. So that's sort of indicated that it's right up here, and then basically you have these pieces tumble down due to gravity and create what we call a talus slope down here. So this is most effective in mid-latitudes. Remember, mid-latitudes are like where we live. You're not close to the equator and you're not close to one of the poles. Instead, you're in the middle. So remember, the equator is 0 latitude and the poles are 90, either north or south. We are around 40 degrees latitude. So why is this most effective in this place is because of the fact that we have winters where for several months the temperature during the day will often get slightly above freezing, but the temperature at night will get slightly below freezing. When the water freezes and pushes the cracks open, it's a very strong force. It's equivalent to hitting the rock with a sledgehammer. But if it only happened once, that wouldn't be such a big deal. But when it happens every night for months at a time, it has a strong effect on the rocks and can do a lot of damage to the rocks. If you go way up north near the poles, the temperature goes below freezing and stays down there. If you go towards the equator, they don't get below freezing very often. So this can affect all rock types. All rock types usually have water in them, and that water can freeze to ice. This is a photograph of a rock that has experienced this. Usually rocks experience multiple types of weathering, but in this case you can really see very clearly that frost wedging, pushing these cracks wider, has been the most dominant type of weathering. And this is also why we get such wonderful potholes in these areas in the mid-latitudes. Basically, water gets in cracks in the roads, freezes, and makes the cracks wider, and this pushes pieces of pavement up. And then when someone comes along and puts a patch in that, there's still a crack between the patch and the original pavement. Water gets in there, freezes. The next time a plow comes by, it just pulls that patch right out. The second type of mechanical weathering is very similar, except in this case, instead of crystals of water growing in the cracks from water freezing, it's when crystals of minerals grow in the cracks in rocks. The growth of a crystal can also be strong enough to push the cracks open wider. Normally, in most cases, it's crystals of salt. So this ends up being most effective along the coastlines because that's where we have salty, humid air. So salt can be, if you've ever walked along the coastline, like, I don't know, Myrtle Beach in South Carolina or in Georgia, you can kind of smell the salt in the air. So the air itself is very humid, has a lot of water vapor in it and salt. At night, when that water vapor cools down, it precipitates out and becomes a dew, same kind of dew we find on the grass in cold mornings here. And then when the dew evaporates the next day as the sun comes up, the salt crystals are left behind and they grow from that water and they can push the rocks apart. This also happens right along the water's edge when you get salt water from the ocean splashing up onto rocks and then drying out and leaving the crystals behind. One place you can see this really effectively is in Cleopatra's Needle, which is an obelisk that was moved from Egypt to Manhattan, Central Park. So this photograph on the left, the black and white photograph, was taken when the obelisk was still in Egypt. And it was 3,500 years old at that point. So you can still read the hieroglyphs really nicely on it. Egypt is a very arid environment. It's extremely dry. When the obelisk was moved to Manhattan, it's now in a very humid environment, and in just 100 years you can see how it's much more difficult to read those hieroglyphs, and that's because of the weathering that has happened that didn't happen in Egypt over the last 3,500 years. The last type of mechanical weathering we're covering goes by several different names. It's called sheeting, it's also called unloading, and it's sometimes called exfoliation as well, and we'll talk about why that is. So this one is most important for plutons. Plutons, remember, are rocks that were formed, igneous rocks that were formed underground. So igneous rocks that formed deep in the crust. So that's what we're seeing right here, right? This is a Pluton. It's got a bunch of rock basically sitting on top of it, and that rock is pressing down on it. That's the way the Pluton formed, so it's happy with all that pressure on it. But over time, the rock up here begins to erode away, and that releases some of that pressure. And what that causes is an expansion in the Pluton. So the Pluton begins to basically push out and up. And they're showing that down here with these red arrows too. This expansion happens long before the Pluton is actually uncovered by erosion. And when that happens, that expansion, what it causes are cracks along the Pluton, and the cracks tend to form parallel to the surface or the outer edge of the Pluton. So the first step basically is that we have the Pluton that formed deep in the ground under all this overlying pressure. The next step is the beginning of erosion, which decreases some of that pressure and therefore causes the Pluton to begin to expand and form cracks. So then eventually, after the cracks have formed, the Pluton is completely uncovered, right? So now we have no more pressure, no more rocks lying on top of the Pluton. But that means all these cracks are exposed at the surface. And what happens then is that pieces of rock on the surface begin to break off. But they break off in these large slabs of rock, almost like the rock is losing the outer part of its skin. And that way of losing outer parts of its skin is because of the way the cracks formed from the decompression. So this takes a long time, and trying to indicate that here with this figure, right? So the Pluton is underground under all this pressure from the rock on top. And then much later, we go from dinosaurs to jeeps, the rock is exposed, and all of these cracks that are forming here are beginning to make these slabs of rocks which break off. So this is called sheeting because the rocks come off in sheets. We'll look at pictures in a moment. It's called unloading because you have basically removed the pressure of the overlying rocks. And it's called exfoliation because that term just means losing a layer of skin. And this final shape that we see exposed at the surface that we can walk around on is called an exfoliation dome. So what kind of rock is going to have this kind of weathering? It's got to be a rock that forms a Pluton, right? Because the whole premise of this is that you had a rock that was deep underground and formed that way, so it was fine under all that pressure until the pressure started to be removed. So granite is the most common form of Pluton. Remember, that's because felsic magma is very thick, and often, most often, it never actually makes it to the surface to erupt. So we end up with a lot more granite plutons than we do felsic rock erupting from volcanoes. These are some pictures of exfoliation domes. So you can see these layers of rock here that are basically like the rock losing skin. Again, on here. This causes a very rounded type of weathering. So you can see there's sort of a rounded edge here, and that's very typical of granite plutons when they weather, because they weather by losing these layers. This is one of the most famous exfoliation domes. This is Half Dome in Yosemite. And again, you can see that rounded effect here. That's because the pluton was rounded, and now it's losing all of these layers from those cracks that were created when erosion began to remove some of the material from on top of it. Okay, on to chemical weathering. So chemical weathering involves reactions that actually destroy minerals in rocks and then sometimes actually create new minerals as well, so secondary minerals. Usually it's because the minerals in the rock are reacting with water, either rain or groundwater. But this water is a little bit different from pure water, right? So pure water is just H2O, but rainwater is slightly acidic. The acid that's in rainwater is called carbonic acid. It's a natural acid that occurs in our atmosphere because we have water vapor in our atmosphere and we have carbon dioxide in our atmosphere. So when you combine those two things, you end up with carbonic acid. It's not acid rain, okay? Acid rain is nitric acid or sulfuric acid. That's not what we're talking about here. This is the same acid, though, that you find in carbonated drinks, because that's another place where we have basically dissolved carbon dioxide into water. So the first type of chemical weathering reaction is when we dissolve a rock, and so therefore it's called dissolution. So in this case, a mineral is destroyed, but there's no secondary mineral, right? This means we leave holes, basically, in the rock. So we make holes because the mineral is simply dissolved and is taken away by the next rainstorm. There are 3 minerals that are easily dissolved by rainwater, which again, remember, is that carbonic acid: calcite, dolomite, and halite. Dolomite and calcite are very similar. Calcite makes up the rock limestone and dolomite makes up the rock dolostone, but these two are very similar. We're going to talk about these in the next chapter. And halite makes up the rock salt. So all of these are sedimentary rocks, which we're going to get to in the next semester. The next chapter. But in general, dissolution means you have pits and caves because you have dissolved minerals from the rock. A dissolution pit is just a small amount of dissolution, and a cave is when it gets pretty big. So we have living caves and dead caves. A living cave is one where water is still dripping down through it. They make these beautiful stalactites and stalagmites and other formations as calcite basically dissolves and then recrystallizes. More pictures. Again, these are living caves over here where you have those stalactites and stalagmites. This is a picture of Mammoth Cave in Kentucky. Large parts of Mammoth Cave are considered dead because there's no longer any water dripping through the roof. Basically, the roof has been capped with a layer of rock that will not let water through. It's a layer of rock made of clay. And sinkholes are basically kind of a cave. They start as a cave. As you can see down in this diagram, what happens with sinkholes is that you begin to dissolve out a lot of rock in here, creating a cave. And then eventually this overlying rock, that's basically the roof of the cave, gets thinner and thinner because the cave gets bigger, and then eventually it caves in. So you can see here we've basically lost the roof of the rock, and that's what creates a sinkhole. Now, not all sinkholes are caused by natural processes like this. Sometimes they're caused when you have a water main break underground, and that leaking water can also basically dissolve away a lot of material. So in that case, it tends to be a faster process. Cave development is a slower process and only happens with certain rock types, right? So we can dissolve calcite in limestone, and we can dissolve dolomite in dolostone, and we can dissolve halite in rock salt. But if you have granite as your bedrock, that's not going to dissolve, so you don't develop sinkholes where you have a lot of granite. Where we live, we have a lot of limestone and dolostone, and we do have small sinkholes around here. Second weathering reaction that's a chemical weathering reaction is called oxidation. Oxidation is simply when you have a reaction between oxygen and some other element. In the case of the oxidation of rocks, it's usually iron. So the oxygen is in the air and the water. The iron is coming from minerals that have iron and often usually magnesium in there. So these are the ferromagnesian minerals. So those are the minerals that are going to be the ones that are easiest to destroy or weather through oxidation. So remember, those included olivine, pyroxene, amphibole, and biotite. Right. So this reaction destroys the ferromagnesium mineral, but it does also create a secondary mineral. So it creates iron oxide minerals, which are a whole group of minerals. And the one that we learned, the example that we learned when we were talking in chapter 3 about minerals, was hematite, which is an iron oxide, right? So iron oxide minerals, we've got iron and oxygen. But there are more iron oxide minerals than just hematite. So we have a whole group of those minerals that can form, but the only one that we've learned and talked specifically about is the hematite. So which rocks will this be most effective on? Any rock that contains ferromagnesian minerals. So that means the mafic rocks, right? Mafic igneous rocks contain the most ferromagnesian minerals. So these are the ones that are going to be most affected by the weathering reaction of oxidation. We can see that in this layer here. See how reddish this layer looks that's been kind of exposed running through here? We're seeing the reddish tint of hematite in what's been weathered out here. That is basically showing a layer of weathered basalt. Basalt is one of the mafic rocks. It's a lava flow. So as it weathers, it tends to create this kind of reddish soil. Same thing's true on the surface of Mars. This is a photograph taken by Curiosity, the most recent rover. Mars is made mostly of basalt. So the surface rocks are mostly basalt, and when they get weathered over a long period of time, they create this very red kind of sandy soil. The third reaction is hydrolysis. Hydro means water, so this is a reaction between water and feldspar minerals. So in this case, just like with oxidation, we're destroying a mineral, but we're also creating a secondary mineral. This is when clay minerals are created. And clays are also a group of minerals, okay? So you can have many different kinds of clay minerals. We're going to not learn specific clay minerals. Instead, we're just going to consider them as a group. They're very stable minerals because they formed at the surface of the earth under surface temperatures and pressures. So this literally is the clay that you would find in soil. It's the kind of clay that is quarried to make different kinds of pottery. There are different clays, different clay minerals that are in different kinds of clay that people use for pottery. So the rocks that are going to be affected in this way, the ones that are going to make clay by destroying feldspars, are going to be mostly granite, because granite has more than one feldspar. Remember, granite was made of quartz, which is not a feldspar, and the sodium-rich plagioclase feldspar and potassium feldspar. So these two are both feldspars. So when you weather granite, you're going to make a lot of clays through this hydrolysis reaction. These are just photographs showing some of that clay. Clay tends to be whitish in color, so here is patches of clay that are being created on this granite boulder, and here we can see a lot of clay being formed here as well on these rocks as they're weathering. So just to recap that, we had 3 mechanical weathering processes, right, where only the rock was only broken down into smaller pieces. And now we've had 3 chemical weathering processes. The first one, dissolution, simply dissolved minerals away. The second 2 both destroyed a mineral and created a secondary mineral that was left that we could see later where the rock had weathered. Differential weathering is just a way of saying that different rocks weather at different rates, and depending on their location, the weathering rate can change as well. So different rocks mean different mineral compositions, and climate is basically the situation in which the rock is existing. Is it in a wet climate or a dry climate, cold climate, hot climate? These things can affect how fast different rocks will weather away. So for instance, in a tropical rainforest, we have a lot of water, and in general, things are pretty warm. Turns out that warm temperatures are good for chemical weathering. So if you increase the temperature by about 10 degrees, you actually double the reaction rate of those chemical reactions. So in general, we will have pretty fast weathering in some place like a tropical rainforest. In a desert, we have heat but no water, right? So plenty of heat, no water. So we're going to get fairly slow weathering there. In Antarctica, we have the opposite. We have lots of water, right? But it's not actually liquid, it's ice. And so since it's ice, it's not going to react with minerals the way that liquid water does. So once again, slow weathering. This is one of the reasons why you develop really good soil profiles and growing conditions closer to the equator, because you end up with warmer, wetter conditions, and that basically just destroys the rocks at the surface more quickly and gives you a thicker soil. So that was climate. What about mineral composition? Well, we've already seen that certain minerals will weather away by certain reactions, right? So, for instance, we've got 2 headstones here. This one is made out of granite, and this one is made out of marble, which is like limestone. It's a calcite-rich rock, right? Calcite was one of those minerals that would dissolve. So calcite actually gets destroyed pretty quickly. And we can see that even though this headstone is younger, 1872 versus 1868, it's much more difficult to read than the granite one. Granite has the feldspars, and it will be eroded by hydrolysis. But it also has quartz. And notice in all of the chemical reactions we've talked about, we haven't mentioned quartz. Quartz is very resistant to weathering, so it lasts a long time. Something else that plays an important role in how quickly different minerals will weather is their shared oxygens. So this is specific to the silicate minerals, the ones that create the igneous rocks. But it turns out that the more shared oxygens a mineral has, the more resistant to weathering it is. So shared oxygens actually go along with crystallization temperature, right? We have very few shared oxygens with the higher crystallization temperatures, and we have lots of shared oxygens when you get down to the lower crystallization temperature. So remember, olivine in particular was just individual tetrahedra, no shared oxygens at all. Quartz is down here at the bottom with lots of shared oxygens and very cool crystallization temperature compared to other minerals. So this is why it's so resistant. Very strong mineral. Lots of shared oxygens. And none of the chemical reactions that we talked about have any effect on quartz. So that should answer the question of why so many beaches are made of white sand, right? These are quartz sand beaches. So where does beach sand come from? It does not come from the ocean. Beach sand comes from this direction, from the continents. It starts out as broken pieces of rock in the center of the continents or in mountains. Those broken pieces of rock get moved, transported, usually through rivers, all the way to the coastline. And all during that time, the minerals in those broken pieces of rock are being weathered away. They're being broken down into smaller pieces, and the feldspars and the olivines and the calcite is all being destroyed through the weathering. The only thing that isn't destroyed is the quartz. And so we end up with a lot of quartz making it all the way to the coastlines, and that's what creates these very nice white sand beaches.